Uh, Hello. This talk is about a programming language that takes all the novel fun out of writing replicated data store applications. So first, a bit of motivation. Why do we care about distributed applications? Well, distributed architectures are really required more and more for any kind of software that people rely on. That's because they can survive changes in the environment that they're running in, whereas centralized services can't. I mean that in several ways. They can survive massive growth in the population using them. They can survive deteriorating infrastructure and being sort of thinly extended. And they can survive being expanded over distance in terms of where they're being used. So today that's like continents, but tomorrow it might be a little farther. The main takeaway is if you're writing code that you want to be used in the future, you should probably think about a distributed architecture. So a great model for distributed architectures is pretty simple, is replicated data stores, where you have a number of machines that each store a full copy of some kind of data, and they support operations on that data. And operations will produce effects that propagate through the network as possible. Now, all kinds of bad things can happen in a distributed network, such as partitions that block messaging between computers and failure of nodes. But the great thing is that in this model, we can continue doing work on replicas that are still running, and they can just hold on to their results and pass them around later. So this property is called availability, and it's really the reason that we deal with this at all. So what does programming look like in a replicated data store system? Well, let's take a step back and think about like what's an important part of programming. Really, the most basic kind of thinking we might want to do about programming is pre- and post-condition reasoning. So if I have a program, I probably want to know about, given some input, what's the output going to be like. Every programmer has to learn how to do this like informally, but there are some formal systems. We saw a little bit about Hoare logic in the last couple talks, but my favorite system for this is dependent refinement types, and in particularly the recent model of liquid types. So here's an example of that where we have a sort function. We want to say that if we take in a list to sort, the list that we put out is going to have the same length as the list we got in. That's an example of the input determining something about the output. And so what does this look like in the context of a replicated store operation? Well, we want some sort of conditions on the state of the system before our operation starts to determine the effect and return value that the operation returns. So let's look at that. This kind of property is consistency, which is kind of the other important thing we want about our programs. So if we look back at our network and we want to run a withdraw operation, the withdraw can look at the pre-store, so that's the state of its store before it starts, and see that there's enough value in this account or whatever to actually withdraw, and so it'll produce like a subtracting effect and a return value that says it did it. So that value 5 is one pre-store, but there are more pre-stores than just that one. As that effect propagates through the network, everywhere it applies becomes another pre-store that we have to consider. So now we've seen the value 5 and the value 4, and if it keeps on going, we might see the value 4 again. But if this other node picks now to wake up, we might see a 1. And since we're subtracting 3, that might cause a problem. Because a pretty basic invariant we probably want about this is that we don't see any negative values on stores. So what could we have done to fix this? I suppose we could have waited for that node over there to unfail, but who knows how long we could be waiting for that. That seems like it would violate the property of availability we talked about earlier. So how do we get both consistency and availability? Well, we can't, sorry. Thanks to the cap theorem, it's just impossible. Essentially, it comes down to if we have partitions, which are given in a distributed network, then we can't have both consistency and availability. And it's pretty simple. Partitions say that we may never get our complete input. Consistency says that our output has to depend on our complete input. So availability, which is that we have to get an output, we can't have that if we might never get an input. So, well, that's a problem because we want all three of these properties. So what do we do about this? Well, partitions are sort of always there, but consistency and availability can be balanced based on different parts of the application that need one or the other. And the way you sort of manipulate this is to change this definition of a complete input. So you have kind of a slider between full availability, where a complete input can just be empty, and full consistency, where the complete input has to contain all those pre-stores that we saw in the example. So no balance is universal because both ends of the spectrum have a pretty important cost. So you kind of always have to answer this question over and over again every time you're writing a new component of any new application. And these definitions of complete input are really consistency levels. That's what they're usually called, so that's what we'll call them. But because there is no generic universal balance, this puts a burden on the replicated application programmer. And it gives them some special tasks that a sequential programmer does not have to deal with. So first is they need to constantly configure new segments of their application to enforce particular consistency levels that they choose. And second, they have to verify that those consistency levels actually connect to the application properties they want, which might be a hard problem depending on how the consistency levels are defined. And that gets to kind of a third task, which is more for the library or framework developer, but that's to come up with a domain of consistency levels that's actually useful. So our contribution is Karol, which is a programming language that simplifies these special tasks by kind of flattening them into just extra rigorous sequential programming tasks. In particular, it requires only local and sequential reasoning from the programmer, and it supports a dependent refinement type system based on liquid types, which is something that is usually only seen for sequential programming. And this is made possible by our other contribution, which is a replicated store runtime design. So let's look at the language, and let's write an ATM application to describe it. This is kind of the simplest replicated data store example. So there's two sort of interesting terms that are in Karol, and Karol is an extension of the lambda calculus. So it's really an extension of lambda calculus with these two terms. So the first is issue, which we can use to make a deposit. So here we have a function that takes an amount to deposit and then produces this operation that issues add n, which is a effect that is defined by the underlying store data type. And so this is what will be sent around to the other replicas, and then it returns n. That's what that in n means. We can check our balance using the other interesting term, which is the query term. So query takes a store value, not exactly sure which store value yet, but a store value and binds it to x. And so this just takes that, binds it to x, and returns it. So how do we safely do the withdraw? Because that's what caused our problem in our example. Well, we can combine the two to create a function that takes an amount to withdraw, and then checks if the store has enough money before issuing the subtraction that would actually do that. Otherwise, it'll return a 0 to say it did nothing and issue no effect. But this isn't really going to help us, because if we ran this in our example we saw at the beginning, it would do the same thing. It would check the store, see 5, and then just do the withdraw, even though there was that store with only a value of 1 sitting around. So what we do here, how we add consistency, is by annotating the query with a consistency guard. In this particular case, it's this LEQ guard that's defined, again, by the underlying store type, which says that x is less than or equal to all of the pre-stores. So this fact is something that as soon as a value is bound to x, this fact is guaranteed to hold for that value by the runtime for the duration of this operation until it terminates. And so as a programmer, you can look at this and you can say, great, I know a fact about x that now I can reason about whether my use of x is safe in this. So that's special task number 1. That's how it's solved, is annotating with consistency guards is how you control the consistency. So Consistency guards are a consistency domain based on data refinements, which is quite different than the usual notion of a consistency level, which is usually a set of possible execution traces. And guards are a little nicer because they're really clear on what they actually guarantee. It's quite a ways to go from a set of execution traces to what actual data properties those imply. And it enables local reasoning. So the meaning of X has the property LEQ in an operation doesn't depend on what other operations have been written or might be running in the background. Any kind of interleavings of them, we know they'll respect this fact, and so we don't have to worry about it. So that's pretty helpful if, say, you're not the only one developing your application. You don't need to know about the behavior of everything that your colleagues wrote. So this is special task number 0, essentially. This is our model for consistency level definitions. Basically, whenever you come up with a new data type, again, this is sequential because all you have to think about is what facts would a programmer want to know about this data. OK, so that kind of gives a sense for the informal way of reasoning about Karol operations. But the really great thing is that we can actually formally reason about them using a refinement type system. And so the types look like this, where a term T has a type operation of D, which is a conflict-aware replicated data type. So that's the thing that provides the effects and guards. It's different from a normal replicated data type, which usually only is concerned with the effects. And then we also have this formula over these special free variables, S, E, and R. So S refers to, abstractly refers to any pre-store. E is the effect, and then R is the return value. So deposit can have the type where it's a function taking an amount that then produces an operation with the effect of adding that amount. And it's over the counter card, which is the one that lets you add and subtract and so on. Balance is pretty simple. It's just an operation that has no effect. And we might want to say something about the return value, but we actually can't because we didn't use a guard in that one. Also, everything that's not a function term is an operation, so that's kind of fun. So the real problem is, how do we verify something that is like non-trivial? So like withdraw. So we want 2 properties in our refinement type on this. One is that the account never goes below 0. That's our main invariant. And the second is that we want the return value to correspond to the actual effect. So we can't cheat and say, well, maybe the effect will change later when it gets to other stores and finds out that it can't actually run there. Because if this is going to be an ATM, of course, it has to return and like spit out money, and it can't take the money back. So this is the way of enforcing that. So again, we have our withdraw operation. And this is basically what the type checking looks like for it. The important rule here is for the query term, where we just add X to the context and include that refinement that we have about X based on the guard that we used. So if you've seen like refinement typing rules before, this looks a lot like just the rule for a like a lambda term. And yeah, that's basically it. There's no concurrent logic going on here, except that we're talking about this sort of universally quantified S value and just putting constraints on it. So this is our Karol solution to special task 2. And it's also very sequential in nature. So this all sounds really great. It sounds like we've just completely abandoned concurrent reasoning, and replicated data store programming is just like normal single-core programming. But there is a cost, and that is, while the programmer can benefit from all this stuff, the runtime needs to know a little more information. The consistency levels we defined have moved much closer to the programmer by being data refinements, but they've moved much farther away from what the runtime would need to know about. So the way we deal with this is we take all the effects and the guards that are in this closed card data type, and we analyze accords between them. So the main theorem here is that if a guard is in accord with an effect, then a query using the guard can safely skip instances of that effect and still be valid. And that's the basic idea. So then you can allow those effects that are in accord to sort of do their own thing in the network while you have this guard taken. So OK, if we still have to do concurrent reasoning, what have we actually gained here? Well, accords are against like the standard way of doing this, where you kind of just verify the whole application in a concurrent context. This way of doing it with accords is better because we have less code to deal with. We're only dealing with like sort of the primitive effects and guards on some kind of data type with no sequential code in there. And it's more reusable because these effects and guards can be used in lots of different applications with lots of different like notions of safety. So traditional models on the left are models on the right, where we can actually take all the sequential code out and verify it individually in the sequential context. And we can define lots of different operations for lots of different applications and keep using this central core as like a library. So all programmers operating on this right side of the thing never have to touch the concurrency. So future work on this, we implemented a runtime system, pretty simple, that runs Karol operations safely. But we only like sort of touched the tip of the iceberg on what this design could look like. So in our model, effects are always you can always emit an effect by default, and you only have to coordinate if you're taking a guard. But maybe in some settings, you'd want the opposite of that, where guards are free until someone emits an effect. Or maybe you want some kind of mix of this. So that would be an interesting thing to follow. Contention management. So if many operations are all trying to do emit and read on mutually exclusive guards and effects, how do you decide, how do you like get everyone making progress? In our implementation, we studied kind of like a TCP congestion control model and also like a turn-taking model. And then the other way would be beyond. So the nice thing about these ones is that you don't have to change the language in order to fiddle around with this stuff. But we could also extend the language to add different ways of coordinating that would maybe be cheaper in some circumstances. So in conclusion, Karol's a nice language for replicated store programming. And it has 3 very distinct technical intrigues to it. And we have an implementation in Haskell that you can check out. It's free software. Thank you.
So let me do the traditional first question from Slido. Someone wants to know what are some examples of, I think, commonly used consistency levels from the wild that you've modeled in your system, and how do they look formally?
Sure. Well, the most basic are strong and weak consistency, which essentially are the 2 ends of that spectrum I showed. There are, if you're not thinking in terms of like the data constraints and stuff, there are sort of like even weaker notions of consistency below the end of that spectrum. So eventual and causal are 2 important ones that we just sort of assume because they don't actually break consistency if you've read about like CRDTs. But like a simple example would be to say executions cannot have 2 withdraws that are concurrent. But to define that, you have to have already defined withdraw, and now you have to connect that to what will the withdraws do.
Phil.
So could you go back to your first example? I wasn't quite clear on how that was. Oops. Could you go back to your first example? I wasn't quite clear on how that was resolved by introducing a guard.
Yeah. So this would be the withdraw. Sorry. Slides. OK. So this would be right. This one, I assume?
Yep.
Yeah, so by introducing the guard that says x has to be less than or equal to all of the possible pre-stores, here 5 is the value that's being bound to this x. But in fact, using that guard would require the runtime to coordinate with the other nodes and find that 1 value, and instead pass that in as like the lower bound on pre-stores. So that does not fit with availability, but in the case of doing the withdraw, it's something that you need there.
So what you're saying is your solution in this case is, no, I can't take out my money because an ATM somewhere else crashed.
Yes.
And how would you really solve this?
Well, you would probably have some kind of reservation system where certain ATMs know that they can deposit up to some reasonable amount, or you might have some more like central bank nodes that the ATMs are calling into, so you assume that these 3 central bank nodes are always going to be up, and they could hold onto that reservation system. But you'd probably want to use some sort of language like this to program those systems.
Okay. Last question, let's do Derek in the back.
Yeah, hi. So maybe I missed this, but how do you prove soundness, or what exactly is the scope of the soundness claim for this type system? Is it including the runtime system as well? And if so, how do you prove this?
Yeah, so the soundness is based on a, so our semantics for the language is sort of in these 2 parts, where we have the sequential semantics of evaluating a karol term, which are non-deterministic because you just sort of take any value to answer the queries. But then you take the things that those produce and put them in an abstract execution where you have a series of events that are related by visibility and so on. And so then our requirement there is that the values chosen for to answer these guards have to fit with sort of any possible interpretation of what came before that event in terms of like the other effects that have been performed. So we have an abstract execution model that we're checking the guards against.
Okay, but do you actually have anything connecting the abstract execution model to the runtime?
No, the abstract execution is very abstract, and the language semantics are very abstract. We have in the paper a sort of runtime design that's like, it's not actual code, but it's like towards there, and we have a soundness proof for that. But it's a little more complicated.
Okay, let's thank Nick and transition to lunch.